Okay, so let me continue the discussion of our matrix structural analysis. Okay, and during the last lecture, we have been able to isolate, okay, KFF, which is the structure stiffness matrix, but specifically associated with free. That's the key word here, DOFs. Okay, and we saw how to develop equations of the form KFF UF equals to PF, okay, where these are the free displacement DOFs, right, and these are the nodal forces applied at free degrees of freedom. Okay, and so after that analysis, we went through post-processing steps, right? Okay, where given UF, okay, from the above. Okay, so you do resolve your structural system. You find the displacements corresponding to a set of loading conditions that you impose. Okay. Then you do two things, right? You do element state determination. Okay, where you answer questions such as whether your element's in tension, compression, and the magnitude of the force. Okay, and you also looked at another important quantity, other support reactions. Support reactions, okay, and the way I presented things, right, is if you look at the element state determination, it's pretty algorithmic, okay, right? So if you do the element state determination, you basically get UF, right? Then for every element you convert it to delta, okay? Its local displacement state, right? Then from delta you convert things to the prime, right, to the local coordinate system. From the local coordinate system you convert to the global, to the element basic system, right? And then you use the relationship F prime, right, in the basic system equals to EA over L, right, for that element times delta prime E. Okay? And again, as you can see, you know, the steps going from there to there would make use of the idea array. The step going from there to there would use the rotation matrix. Okay, the step going from there to there would use the RBM matrix. Okay, and the step from here to here will invoke sort of the element level constitutive law. Constitutive law, okay, which is actually derived from the differential equation. Okay, always remember there is a differential equation that's being solved in the background as you're going through these motions. Okay, now when I presented support reactions, Okay? We're actually forced to go and draw free body diagrams, right? The FBDs, and you guys have, you know, it brings back memories of courses like 310. And as you can see, a lot of, you know, we used a lot of geometric arguments, sines, cosines, but it wasn't really algorithmic, okay? And of course, when you write, you know, general purpose structural analysis code, you want your program to kind of spit out to you the support reactions in a completely automated way, and which is applicable to general situations. Okay? And so this motivates the following presentation, right? And in fact, what I'll show you happens in, you know, in real codes, whether these are sort of these structural analysis based codes or finite elements. So there, you basically, you write down the expanded system. Okay, and so we're going to cover material that starts on page 244, okay, and goes on. I'll present it in slightly different order, in my view, in a more efficient way. Okay, and so the expanded system, right, looks at a full structure. Okay, K U equals to P. Okay, where we take into account all degrees of freedom, okay? Whether these guys are restrained or whether these guys are free, okay? Right. Then the above system can be rewritten in terms of the following submatrices and subvectors. I think I hinted at that in prior lectures, but let me repeat this here. Okay. In the upper left-hand corner, okay, you have your old friend KFF, okay, the structure stiffness matrix that couples all the free degrees of freedom. Okay. In this part of your unknown vector, you put your UF, right? And in this part of the forcing, nodal forces, you put PF. Okay. Then you populate the rest of the displacement vector by UD, right? Remember, these are the displacements at the prescribed degrees of freedom. And here you put your PD, okay, which are sort of forces acting at the prescribed degrees of freedom. In other words, exactly your support reactions. Okay? And then you populate the rest of the matrix as follows. Right? You have the two coupling matrices, KFD and KDF, right, that couple free and restrained, and then restrained and free degrees of freedom. And finally, you have your KDD that couples the restrained degrees of freedom. Okay? So this is the this is sort of the expanded matrix, and this is in principle what gets programmed in real situations. Okay? Now, to simplify the discussion, let me write this matrix out, right, as two systems of linear equations. Right? KFF goes multiplies UF, okay, plus KFD goes and multiplies UD. The end result is PF. Okay. And then another system that you're satisfying simultaneously. KDF times UF plus KDD times UD equals to P sub D. Okay. Right. And then, if you look at the expanded system, okay, at that point you have not incorporated any of the boundary conditions. Okay? And so if you look at a system like this, it will not have solution, as you would expect, right, of the form k minus 1 p, right? Because, again, part of u is ud, right? So how do you guarantee that the restrained degrees of freedom are satisfied, okay, as far as the displacements are concerned? And second, the k itself will not have an inverse, okay, because it's, as I said, lacking the boundary conditions. So all of the translation modes and rotation modes are going to be in k, right, which means that there's no way to uniquely obtain your displacements, okay? However, this decomposition leads to a structure, right, that I'll present in a second, right? So we partition the matrix system like this, right? We rewrite the individual equation systems, okay? And first, let's concentrate on this equation first, right? So here I go, right? I have KFF, UF, right? So K I compute for my given structure. UF is unknown. Let me keep this on the left-hand side, okay? And then let me take this term and move it to the right, okay? E equals 2. So I have PF minus KFD UD, okay? Right? So let's look at the terms carefully. These are the prescribed forces, right, at free DOFs, okay? So this is given, okay? That guy, KFD, you obtain by using, direct stiffness assembly, right? And UD are also the prescribed restrained DOFs, okay, for displacement. Okay? And so UD can take on, okay, several values, right? It could be truly zero if zero displacement is prescribed, okay? But it may not be zero, okay? If non-zero displacements are prescribed, okay? Right? Supposedly you're doing some kind of a bridge structure like this, right? You have your cables going down, right? And then you say, look, I know that over time, right, some conditions maybe about your soil or whatnot, right? Or you're trying to come up with different scenarios. You say, okay, you know what? Let's say within the first year, I know that this node here will settle, okay? And this is going to be my new location of this node. So then you prescribe non-zero displacement here, okay? So what's going to happen is this non-zero displacement is going to go and multiply the KFD, okay? Right? And will provide for you what? A force due to non-zero displacement. Okay? So this will come in as the additional forcing for the structure, right? And so now it's interesting, right? If you look at this equation set, you're consistently accounting for the forces that are applied directly to the structure, right? And forces that are applied indirectly to the structure due to the motion of supports. Okay? And now you know that although your K is not invertible, KFF is invertible. Okay? And so you can solve the top equation system for UF as follows. Right, your UF equals to, you take the KFF, you take its inverse, okay, using, whatever linear algebra methods that you're familiar with. And MATLAB it'll do what it'll do, okay? And that multiplies PF minus KFD FD UD. Okay? And so this becomes your solution now. Okay? So now that you have UF, okay, you need to do two things. You go back and do the element state determination. Okay, and then nothing changes here. Okay, you still go element by element, you pass down the displacements, right? You apply the force displacement relationship, and you have your forces. You know if you're in tension or in compression, and how much force you have, and whether you're exceeding, the amount of force that a given element can support. Okay, and then how do you get support reactions? Okay, for support reactions, you need to go back to your two equation systems. Okay, and now work with this equation here. Okay, let me write it out again. This has to hold too. KdF UF plus KDD UD, right, equals to PD. So what do you know here? Okay. Well, KdF, as before, you assemble using direct stiffness assembly, okay? But using a full set of degrees of freedom. Okay? I'll show you in the example. KDD, the same thing. Okay. UD, you know, because these are your prescribed displacements. Prescribed displacements. Okay, and UF, you know, because you just solved for it. These are free DOFs for which you just solved. Okay, so you know everything on the left-hand side. Okay, and guess what? PD is exactly your support reactions that you don't know. So you basically write PD equals to KdF UF plus KDD UD. Okay, and so see the power, right, in this expression. You don't need to go to every support node, right, and draw a free body diagram and try to figure out, what is the force that sort of balances out, right? This entire set of operations is encoded in this expression here. Okay, right, and so this is very easy to do on the computer. You have your UF, you have your UD, you pass them down, you multiply by KdF KDD, which you've assembled, and then you report PD. Okay, very simple. No need to draw free body diagrams or try to understand what's going on. Okay. All right, so what I suggest we do next is we'll look at our example, our two-element example. Goes a long way. Okay? If you recall this guy, this was our element A, this is element B, right? This is node 1, this is node 2, this was node 3, right? This guy was subjected to the force acting in this direction. Right? These were the degree of freedom, global, U1, U2, U3, U4, right? U5, and U6, right? And so this is the